For any help regarding magnetic materials assignment help, visit https://www.eduassignmenthelp.com. Email info@eduassignmenthelp.com. Call us at +1 678 648 4277. Magnetic Materials Assignment Help. Problem 1. The figures below depict two orientations of domain walls in a uniaxial material. Explain why each is unlikely. Problem 2. Calculate the domain wall thickness and energy density for ND2 Fe 14b and Ni80 Fe 20 from data in CH6, assuming in each case A equals 2x 10 to 11j/m. Problem 3. Solve the uniaxial domain wall problem with magnetoelastic energy included. Work out the solution for three cases: I. Uniaxial strain along the EZ axis, 2. Perpendicular to the EA and parallel to the magnetization at the center of the wall, and 3. Perpendicular to the EA and to the magnetization at the center of the wall. eduassignmenthelp.com. Problem 4. Evaluate the constant in EQ 8.10 for uniaxial anisotropy for the two wall profiles, theta, infinity, equals 0 and pi/2, in both cases theta equals 0. Can you find a solution to the integral equation for the second set of boundary conditions? Problem 5. Write the exchange, anisotropy, and magnetostatic energy expressions for a Néel wall in a film of thickness T. Compare the relative magnitude of these terms. Why does the magnetostatic energy not appear in the minimization of the wall energy per unit area to determine the wall width? Problem 6. Relate the energy of the flux distribution about a sample in a state of remanent magnetization, Hext equals 0, to that of the configuration of least magnetostatic energy inside the sample. Use the I2 or power density analogy. How is this energy minimized? Problem 7. A. Calculate the radius RC of a sphere for which the magnetostatic energy of the single domain state is exactly equal to the energy needed to create a 180 domain wall through the middle of the sphere. B. Calculate this radius for iron. eduassignmenthelp.com. C. Compare this radius with the domain wall thickness delta dW for iron. D. Express RC and delta dW in terms of the domain wall energy density sigma dW and discuss the difference between these two expressions. Problem 8. Calculate the superparamagnetic dimensions for an acicular iron particle with a 10:1 aspect ratio and anisotropy due only to its shape. eduassignmenthelp.com. Solution 1. The first costs more energy because the wall has a larger area than if it were perpendicular to the top surface. The second wall violates the condition of continuity of the normal component of magnetization across the wall. Basically, it is a magnetically charged wall. Charged walls can exist under some conditions when the medium is magnetically hard. A longitudinal recording medium is a series of charged head-to-head walls. Solution 2. The anisotropy constants in J/M3 are listed below with the calculated wall width, EQ 8.15, and wall energy density, EQ 8.16. Solution. eduassignmenthelp.com. Solution 3. The magnetoelastic energy, B1 x2+, simply adds to the anisotropy energy, Qs into theta. For uniaxial strain, the MET energy becomes -2b1 into theta, where theta is the angle between the direction of magnetization and that of the tensile strain direction. The tensile direction becomes a hard axis and the plane normal to it becomes an easy plane if B1 EO0. Thus, for the three cases identified above, the net anisotropy can be expressed as follows. These coefficients replace K in the expressions for wall energy, 4, AK, 1/2, and width, pi, A/K, 1/2. eduassignmenthelp.com. Case I, wall energy decreases and wall thickness increases for B1 EO0. Case 2, wall energy increases and wall thickness decreases for B1 EO0. Case 3, the tensile stress leaves the magnetization in all parts of the wall equally affected, so there is no change in wall energy or shape for this direction of stress. For the first set of boundary conditions, the solution is given in the text. For the second set of boundary conditions, the second integral is, which has for its solutions the elliptic integrals. eduassignmenthelp.com. Solution 5. The free energy density is a function of position x across the NaL wall width. It can be written: we can approximate the average x component of the magnetization across the wall width as equals 1/2, and the demagnetizing factor of the wall as T/delta dW. Assuming a wall width of order 10 to 7 m and an anisotropy of 105 J/m3, and a magnetization of 1 T, the three terms above have magnitudes are 104, 105 and 4 by 105 J/m3, respectively. None is insignificant. Without integrating this function, the energy per unit area can be approximated as, with the wall width treated as a variable. Clearly, this function is minimized with respect to the wall width for independent of the magnetostatic contribution, because in this approximation, the magnetostatic contribution is independent of the wall width. Solution 6. For an electrical circuit, the power dissipation is I2R. For a magnetic circuit, Appendix 2.1, the energy density is phi2Rm equals phi2L/A equals B2 law/equals BHV. In the free space about the sample. eduassignmenthelp.com. BHV is equal to O2V. Inside the sample, using H is almost equal to NMR, BHV is equal to H2V is almost equal to N2 Mr. 2V. This quantity is positive definite and minimized by virtue of the product NMR, which allows larger Mr. if n is small but demands smaller Mr. when n is large. Solution 7. A. Equating total magnetostatic energy for a sphere to wall energy, sigma dW, gives delta dW is proportional to the ratio of sigma dW to the anisotropy energy density. RC is proportional to the ratio of sigma dW to the magnetostatic energy density for a sphere. In the domain wall, it is the strength of the anisotropy energy that increases the energy. eduassignmenthelp.com. Inside the domain wall and therefore reduces the wall width. In the particle, it is the magnetostatic energy that drives the creation of the domain wall. The greater the magnetostatic energy, the less stable is a single domain particle and the smaller is its critical radius. eduassignmenthelp.com.